Okay, so what I'm just going to do is run through a series of theorems that I'm going to prove and show you how I break down the know and the show, so you get kind of refreshed on how to do that. So this is a theorem that was in it was a homework problem, and some of the students had asked me about this specific problem, that if you have an n by n matrix, and you know that the sum of each row is 1, you're supposed to show that lambda equals 1 is the eigenvalue of A. So the first thing is to write down the know. You know A is n by n, so it's a square n by n matrix. It's not a 2 by 2 matrix, it's an n by n. But you'll see as I progress along that sometimes if I'm not sure where to go, I start with a 2 by 2 and try to figure out what's going on with the 2 by 2. But I know that the sum of each row is equal to 1. Now I wrote down verbatim exactly what was stated, but that's not really something I can sink my teeth into. So I make it real. So at every step of the way, when I write down the know, I first copy and paste whatever was between the if and then I have to transform it somehow. I kind of told you formulaically, but somehow you have to have something there that you can grab onto and use to construct a proof. So I wrote out the A, that's n by n, and I actually wrote it out in symbols so I can see it. And what I know is that the sum of each one of those rows is equal to 1. And I write it down there, so it's like having the puzzle pieces all sitting in front of you. My show is that lambda equals 1 is the eigenvalue of A. Well, that means that I have to expand that out. I can't sink my teeth into that either. But writing down the definition that there exists a vector that's not 0, so that AB is lambda V, that's a definition of eigenvalue and eigenvector. But then I make it real in terms of what I already had in the know. That's my A, that's my vector V, and I want 1 to be the eigenvalue. That's what it's supposed to look like. Or if I multiply everything out, that's what I'm supposed to get at the very end. So I keep expanding it so I can really see what my end goal is, and I really know where my start point is. And in the past, when I've written out these proofs for you, I haven't had the slide where you have the know and the show sitting in front of you. But it's really important that you have that know and show sitting out where you can actually use it. You want to go from this part to that part. You've expanded the know as far as you can, and you've expanded the show as far as you can. You have to really get from one side to the other. And then you start doing the brainstorming and looking at it. I think as students you get very stuck on the brainstorming part, that you're I don't think I can write my own proof, I can't. But all that organization part comes first. And I've built that into the structure of how I grade too. All the organizational part gives you most of the points. And the final part gives you the least points, because that's the most important part, is organizing it, making sure you have it all in place. But when you look at these know and show from the right and the left, you see that there's some kind of similarity between this part and that part. This has a sum in it, that has a sum in it. So I look at this part and say, well, it kind of looks like that part, except that part has what in it? Has a bunch of v's in it. So if those v's weren't there, if they were all 1, this part and that part would look the same. So that's how my mind is thinking when I have these two puzzle pieces sitting next to each other. They look alike, but they don't kind of look alike, because those V1s through V2s, all those should be 1 to make them actually look alike. So I need to show that V1 through Vn actually exists. That's part of I have to show that there is a vector V such that blah, 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 blah. So I'm just going to guess all 1s. It's just a guess, because that's the way to connect the two. So let's see what happens if I set all the V's to be 1. Well, look what happens. If I set all the V's to be 1, I get exactly 1, 1, 1, 1, 1, and I get AV is actually V, with V equal 1, 1, 1, 1, 1. It worked out. So once you get to that point where everything's organized and you have everything set up, it is pretty simple at that point, at least for you now. If you keep going higher and higher, there'll be points where you're just stuck. And then you get used to the idea of being stuck, but not yet. Then you have to write it up cleanly, which you might not have, if you have the ingredients there like that on the test, I've usually given you points if you had those ideas, because I know that it takes a little while to write the clean proof. But this is the proof that you see in other classes. You don't see that middle ground, or you don't see that piece where someone was struggling through it. The clean proof is, here's my A. We have by hypothesis that I just wrote it out for the reader to see. We must show, I just wrote this out for the reader to see. We must show there exists a V such that AV is equal to V. And then out of nowhere comes Well, we claim that v equals 1 will work. That's how you usually see it in classes, right? Out of nowhere, somebody pulls something out of a hat. It wasn't really from nowhere. Somebody thought about it in the background in their scratch work, and then they're, oh, now I have it. Now I'm going to write a clean proof, and it'll look like it appeared out of nowhere. And I'm going to claim that that satisfies our conclusion. Watch how I'm leading the reader along. So to see this, well, I just do what I did in the scratch work. I just multiply it out, and I get AV is equal to that 1. And I indicate to the reader I'm using the hypothesis. So I get AV is equal to V. So lambda 1 is the eigenvalue of V with eigenvector. I make it very clear and spelled out. So when you see a proof like that, you look at it and say, well, it doesn't really look that hard. 90% of the effort was just organizing it and figuring out what to do. A clean, good proof shouldn't look hard. It should look effortless. Do we have questions on this last proof? Simple? It's always simple when it's done right.